So dear students, in this lecture we will discuss about the observable canonical form. Observable canonical form is also a tool or a technique through which we can convert a given transfer function of a linear time invariant system to its equivalent state space model. So, see, the purpose of state space analysis is to design a controller, and the controller can be designed using a state space analysis or through pole placement analysis or technique. So we need to check the controllability and observability. And in case of observability, we need to uh, have a controller which can observe the given transfer function. So it becomes important to understand the observability of a given system. And so if we have a transfer function, we can convert that into an observable canonical form, and then we can check the observability. So, so any given, a linear time invariant discrete time system can be represented through the transfer function as given by this equation number 1. Now we can convert this into an equivalent state space model by using this observable canonical form technique, and it is also known as second companion. Okay, the controllable canonical form is known as first companion, it is known as second companion, right? Now let us start with the process of obtaining the equivalent state space model. Let us take this equation number 1. So let us take the case m is equal to n. So this equation yz, it can be written as yz is equal to beta naught z raised to the power n minus, oh sorry, z raised to the power n, and plus beta 1 z raised to the power n minus 1 plus beta 2 z raised to the power n minus 2, and so on. So we have up till beta n, and divided by the denominator part, which is z raised to the power n plus alpha 1 z raised to the power n minus 1 plus alpha 2 z raised to the power n minus 2, and so on, right? Where n is basically the order of the system. So this is, for example, equation number 2. Now if yz by uz, sorry, so yz by uz, this is yz by uz, okay. Now if we cross multiply this one, right, so we can cross multiply, so we will get yz into z raised to the power n plus alpha 1 z raised to the power n minus 1 plus alpha 2 z raised to the power n minus 2, and up till alpha n. Similarly, on this side we have uz, and it is multiplied with beta naught z raised to the power n plus beta 1 z raised to the power n minus 1 plus beta 2 z raised to the power n minus 2, and up till beta n, right? Now we can open up the bracket and multiply this one. So we will get z raised to the power n yz plus alpha 1 z raised to the power n minus 1 yz, and in similar manner we can open up the right hand side also. So alpha 2 z raised to the power n minus 2 yz, and up till, let us say, alpha n yz. Similarly, on the right hand side we have beta naught z raised to the power n uz plus beta 1 z raised to the power n minus 1 uz plus beta 2 z raised to the power n minus 2 uz, and up till beta n uz. So this is, for example, equation number 3. Now what we will do is we will take all the coefficients on the one side and uh, combine the relevant coefficients of z, like zn coefficients will be combined together, zn minus 1 coefficients will be combined together, and in this way we will get a new equation. So let us take all these on the one side. So we have zn yz and minus, sorry, so we have plus, sorry, zn minus 1 alpha 1 zn minus 1 into yz plus alpha 2 z raised to the power n minus 1 into yz plus up till alpha n yz, and we have minus beta naught uh, uz. So beta naught z raised to the power n uz minus beta 1 z raised to the power n minus 1 uz minus beta 2 z raised to the power n minus 2 uz, and up till minus beta n u z is equal to 0. Now we will combine these coefficients, like zn will be combined with zn here, and then we have zn minus 1 with zn minus 1. Here it is zn minus 2, sorry. So zn minus 2 with zn minus 2, and this with this. So we'll combine and simplify this equation. So on simplifying, we will get like this. So we have z raised to the power n, and we have yz minus beta naught uz, right? So we have combined this and this term, right? Similarly, we have plus, then we will combine z raised to the power n minus 1, and we have alpha 1 yz minus beta 1 uz, right? Then we have plus z raised to the power n minus 2, and we have alpha 2 yz minus beta 2 uz, right? And so on. So we have now, we'll combine this term with this term. So we have, this is z raised to the power 0, right? Alpha n yz minus beta n u z is equal to 0, right? So now we will take this is, let us, equation number 4, and we will convert this equation number 4 into uh, in terms of yz only, okay? So we will rearrange equation 4 for yz, though yz will be on both the sides. So we will rearrange it in this way, that we have this yz here, this one, and rest of the terms will be on the other side. So we have, we'll divide this equation with zn. So first of all, divide equation 4 with z raised to the power n. So if we do so, we will have yz minus beta naught uz, right? Then plus z raised to the power minus 1, because here if you see z raised to the power n minus 1 by z raised to the power n, so we have z raised to the power n into z raised to the power minus 1 divided by z raised to the power n. So this is cancelled out, and we have z raised to the power minus 1, right? So z raised to the power minus n, we have this alpha 1 yz minus beta 1 uz, right? Then we have plus z raised to the power minus 2, we have alpha 2 yz minus beta 2 uz and plus so here dividing by z raised to the power n will give us z raised to the power minus n, right? This is alpha n yz minus beta n u z is equal to 0. So this we can remove from here. We'll make some space. So we can write it here. So we have beta n uz is equal to 0. Now we have yz here, and we will take all these terms on the right hand side. Okay, take all these terms right hand side, right? So uh, so why we have yz is equal to, we have beta naught uz minus z inverse alpha 1 yz minus beta 1 uz, right? Then we have minus z raised to the power minus 2. We have alpha 2 yz minus beta 2 uz. We have minus z raised to the power minus n alpha n yz and minus beta n u z is equal to not equal to 0, sorry, it is already unequal, so this is not equal to 0. Now we can multiply this with minus sign here. We can also simplify this, or yz is equal to beta naught uz plus z raised to the power minus 1 into, so this will become plus here, minus into, sorry, minus into minus will give us plus, so we have beta 1 uz, right? Minus alpha 1 y z, right? So we have plus z raised to the power minus 2, we have beta 2 uz minus alpha 2 y z. So similarly we can simplify the rest of the terms. We have z raised to the power minus n, and we have beta n u z minus alpha n y z, right? Now this is, for example, equation number 5. Now we can draw the block diagram of this equation. In this, if you take the inverse z transform, so we will get uh, like here yk. Okay, so uh, to obtain the response yk of the given transfer function, it is given by equation number 1. Okay, so we can take the inverse z transform of equation 5. So however we can use equation 5 to draw the, okay, we can use equation 5 to draw the alternate or alternative of the direct realization realization structure, that is alternative to what we have got through controllable canonical form, right? So now, so let us start drawing this the structure here. So we will write this equation number 5 once again on this screen, right? So the equation 5 has been written here for the convenience. So let us start drawing the uh, direct realization structure or a block diagram representation of this equation. Now, yz, the inverse z transform of yz is yk. So we'll write it here. Yk is z inverse of yz, and uk is z inverse of uz, right? So we have let us say yk, this is the output, right? And because this is the output, so now we have yz is equal to beta naught into uz means uk. So let us take uk here. Okay, so from here we have uk, and then we will multiply uk with beta naught. This is one element, beta naught, and then we will add here, right? So it is added with something which is coming from this side. We have plus and plus, right? So beta naught, yk is beta naught into uk plus something. So here we have a delay. Now this z inverse, this is a delay element, right? This is the delay element, right? This is the delay element. So we will add one delay here. So one delay has been added. So this is z inverse basically, and it will have certain input here. For example, so the input to this would be the output to this would be x and k, right? The output to this would be x and k, but the input will be x and k plus 1. This is the input, right? Now this x and k plus 1, now we have this term here, right? So we have, let us add this term. So we will multiply it here with beta 1 uk uz, you can see here it is multiplied with uk is multiplied with beta n, right? And then we have minus alpha 1 yz, so that means it will be added with one more element which is coming from feedback. These alphas are in the feedback path and betas are in the feed forward path, right? So we will add minus alpha 1 here, and this minus alpha 1 is multiplied with yk, right? So now this is one thing. So now some input is coming here. Now we have, this is also a delay element. Now we have two delay elements. One element is here. Now we will add one more delay element here, right? One more delay element is added here. So let us say that the output to this delay element is x n minus 1 k, right? The output to this is xn minus 1k. However, the input to this delay element is xn minus 1 k plus 1. Now, why we are taking these x as the input and output of the delay element? Because a delay element is changing the state of the system, dynamics. It is representing the dynamics. So it is the change, it is the state that changes, right? The output though depends upon the state. However, the delay element basically bring changes to the state of the system, right? Now we have two delay elements. This is z inverse here, right? This is also z inverse here. Now we have z inverse 2, this one, right? So this is multiplied with this particular combination. So we have beta 2 here. So it is added to minus alpha 2, right? Minus alpha 2. So it is done like this. So I will remove all these elements from here. Now, in this way, in this way we will keep on adding the delay elements. We'll keep on adding the delay elements, and we will have one delay element here, right? And let us say now this one. So uh, we have, this is, let us say, x2, right? And x2k is here. Okay, and the input to this would be, let us say, x2k plus 1, right? Now this is beta n minus 1, and it is added with minus alpha n minus 1, right? And all these elements are somewhere in between, right? So because this is nth order, similarly we have z raised to the power minus an nth delay element here. So nth delay element, so we will add one more delay element, the last delay element here, and the the output of this is x1k. Output of nth delay element is x1k, and input will be x1k plus 1, because delay element is delaying these x k plus 1th state to kth state, right? So we will add. So here we have beta n into uk. So beta n into uk, and it is added with minus alpha n, right? It is added with minus alpha n. So in this way, if you see, you can see here, if you have understood this, we have states here like x n k plus 1, x n minus 1 k plus 1, x2 k plus 1, x1 k plus 1, like this, right? And we have all the elements. Okay, betas are in feed forward path, and alphas are in feedback path, right? So this is the feedback path, and this is the feed forward path, right? This is the feed forward path, right? So from this diagram we can easily obtain the state equation and output equation of the given system. For example, if you see x n k plus 1, it is equal to, x n k plus 1 is equal to uh, beta 1 into uk minus alpha 1 into yk plus xn minus 1 k. So Let us write xn k plus 1. So it is equal to xn minus 1 k plus beta 1 uk minus alpha 1 yk, right? So similarly, if you see, and in this way we have xn minus 1 k plus 1, it would be beta 2 into uk and minus alpha 2 into yk, and then we have, so here we must be having xn minus 2 k, right? So it would be coming from some of the delay elements, right? So because it is not shown, all the delay elements cannot be shown here at one place, so we have taken a break point here, right? So similarly we have xn minus 1 k plus 1, so this would be equal to xn minus 2 k plus beta 2 uk minus alpha 2 yk, right? And in this way we have x2 plus k plus 1. So in this way we'll keep on doing, and we have x2 k plus 1. So it is equal to, as you can see, x2 k plus 1 is equal to beta n minus 1 into uk minus alpha n minus 1 into yk plus x1 k, right? So it is x1 k plus beta n minus 1 uk minus alpha n minus 1 yk, right? And x1 k plus 1 is equal to, as you can see, x1 k plus 1 is equal to beta n uk minus alpha n yk, right? So it is equal to beta n uk minus alpha n yk, right? So it is equal to this. Now if you go for the output, so response, so yk is equal to beta naught uk plus xnk, right? So yk is xnk plus beta naught uk, right? So this is one equation. Now if we substitute yk in all the above state equations, now this is the output equation, and all these are the state equations, right? So if we substitute yk in all the above state equations, we will get the state equations purely in terms of yk and uk, right? So because as of now these state equations are in terms of yk, we have yk term here, so we will replace, fine. So let us see. So we have xn minus 1 k minus alpha 1, and we'll replace it here. So we have x1, so we have xn k and plus beta naught uk and mine plus beta 1 uk, right? So we can open up this bracket. So when we open up this bracket, so we will get xn minus 1 k minus alpha n xn k minus alpha 1 beta naught uk minus beta 1 uk. So we can write this equation as xn minus 1 k minus alpha n xn k, right, minus alpha 1 beta naught uk plus beta 1 uk. So we can take this uk common, and we will have this kind of equation now. So we have plus beta 1, and this is plus, so minus alpha 1 beta naught plus beta 1 u k, this one, right? So similarly we can write for this equation also, it would be x n minus 2k, and we will have uh, so when we put this here, first of all we should correct this one. So this is not alpha n, so this is alpha 1 here, right? So when we substitute yk in this equation, x n minus 1 k plus 1, so we will have x n minus 2 into k plus minus alpha 2 x n k plus minus alpha 2 beta naught plus beta 2 uk, right? And in this way we will have an equation for this also. We will replace yk with the given equation, this one. So we will have x1k, and then we have minus alpha n minus 1 into xnk, and then we have plus, and then we have minus alpha n minus 1 into beta naught plus beta n minus 1 into uk, right? And similarly for this one, so we have you know a minus alpha n x n k, and then we have plus minus alpha n beta naught plus beta n u k, right? So in this way we have got all the equations in terms of, as you can see, x k and u k only. So y k has been replaced here. So now our purpose, okay, so the objective now is to convert the above state and output equations into the standard state space model, which is, we can convert this in terms of this like x1k plus 1, x2k plus 1 up till xn minus 1k plus 1 and xnk plus 1. These are the state dynamics of this given system is equal to, then we will have an f matrix which will have dimensions in n by n by n dimensions will be there. So here we have x1k, x2k, and then we have x n minus 1k, and then xnk, right? All the states are there. Then we have G matrix, which is nothing but it is a column matrix, right? So it is n rows and one column, right? So then we have UK here. Similarly, the output equation yk can be written as the product of a matrix C. So this is C matrix, this is F matrix, this is G matrix. So it is one row into n column, right? And we have all the state vectors from x1k to xn k here, and plus then we have a scalar d right? It is 1 into 1 matrix and UK. So this is the standard form. As we can see, we already have this kind of representation, so we can write these equations in terms of the standard state space. So let us write all these equations. So we have rewritten all these state equations once again, and this is the output equation, right? So we have written all these equations once again, and you can see earlier it was from x n k plus 1 to x1 k plus 1. We have simply rearranged these equations and written from x1 k plus 1 to xn k plus 1, right? So now let us write x1 k plus 1 and x2 k plus 1 up till xn minus 1 k plus 1 and xn k plus 1, right, is equal to, let us take a matrix here. So we write all the state vectors, x1k, x2k, and we have xn minus 1k, and then we have xn k, right? And then we have matrix G, U, K, right? So let us take x1 k plus 1. So x1 k plus 1 has only this state here, and rest of the states are 0. So we have 0, 0, 0. X1 is 0, x2 is 0, and then we have all other state. Xn minus 1 is 0, and we have xn. So this would be minus alpha n. So if you multiply this column vector, this row, so you will get minus alpha n xn. Now plus, so here we have the first element as minus alpha n beta naught plus beta n, right? Then let us come to x2k plus 1. So x2k plus 1 has x1k and then xnk, and rest of the elements are 0 and then uk, right? So x1k into 1 and then 0 up to we have all elements 0. Then we have minus alpha n minus 1, right? So then we have this term, UK term. So it would be minus alpha n minus 1 beta naught plus beta n minus 1, right? Similarly, we'll keep on doing this thing, and eventually we will have xn minus 1k plus 1. So it has xn minus 2k. So we will have 0, 0. So we have somewhere 1, and then we have 0 here, and then we have minus alpha 2, right? And at last xnk plus 1, this one. So we have xn minus 1k. So this term is 0, x1 term is 0, x2 term is 0, and then we have this term is also 0. So xn minus 1 into this is xn minus 1k, and then we have minus alpha 1, right? And here we will have you can see xn minus 1 k plus 1. Here we have this term, so minus alpha 2 beta naught plus beta 2, right? And then we have xn k plus 1, the last term. It has this term in the u, the control variable, so minus alpha 1 beta naught plus beta. We will write the output equation yk. So yk, it is equal to like this. So we have the state vector x1k, x2k, and xn minus 1k, and then finally xnk, right? Now here, if you see in this output equation, this is the output equation. If you see in this equation, yk does not have any of the coefficient for x1k, x2k up till xn minus 1k. So all these will be zero, because your this matrix, this output matrix, which is also this is the F matrix, right? And it has n by n dimension. This is the G matrix, right? And this is n into 1 vector, and then we have, this is the C matrix, right, the output matrix, and it is one row and column matrix, right? So x1 into 0 is 0, x2 into 0 is 0, and in this way we will have 1 here. Xn into 1 is xn. You can see, if you multiply it in this way, you'll get the same equation as the output equation, right? So then we have a scalar value, which is nothing but beta naught into uk, right? So these are, let us say, some equation number, what do you uh, you know 6 and 7, right? So these are the equation number, let us say 6. So equation 6 gives us the state space model, the state space model of the transfer function given by equation 1. Okay, so this is the required state space model. Fine. So so I hope this is clear. So what did we do? We simply had the transfer function as given by equation 1. We have cross multiplied these parameters with one another, yz with the denominator of the transfer function and uz with the numerator. And in this process, we simplified the equation and we got an equation number 5 in terms of yz. So by using this equation number 5, we have developed a direct realization structure through observable canonical form. And from this realization structure, we have obtained all the state equations as given here. So our purpose is to convert or represent these state equations in form of the standard state space model, which is given by equation number 6. So as you can see here, this is the required alternative to the direct realization structure through observable canonical form, and these are the matrices A, B, C, or D. Or simply, since we have used the notation F, and then we have used the notation G and C and D, right? So this is our notation. You can use any notation, A, B, C, D, or F, G, C, D, whatever, right? So this is it for today's lecture. I hope it is clear to you that how to convert a given transfer function to the required state space model using the observable canonical form, which is also known as second companion, right? So this is all about today's class. Thank you so much.